Welcome. This is Organic 1 Practice Test 1. This is where we go through all of the kind of physical properties of organic molecules. So we're going to talk about some big ideas like naming, functional groups, different kinds of projections, trying to see organic molecules not just as drawings on pieces of paper, but as real tangible objects. So let's start with naming. IUPAC naming, everybody's favorite. I'm going to provide a chart that has all the prefixes and suffixes for you guys. So you don't have to memorize all of these, but you'll have to be able to recognize what functional groups are there and whether or not those functional groups deserve to get a prefix or deserve to get a suffix and the numbering that might be going along with that. So here I look, I see, I'll keep it zoomed out. I see a carboxylic acid, I see a ketone, I see an alcohol, and I see an aldehyde. Well, I'm going to look for the highest priority functional group here. So that's carboxylic acid out of all of those options. And so I want to start my numbering to give carboxylic acid the lowest possible number. So 1, 2, 3, 4, 5, 6. That's the longest carbon chain I can make while including my highest priority functional group. So that's what we're going to do. After this point, we have to start naming the prefixes and the suffixes. So anything that is not my highest priority functional group gets to be a prefix. So it gets to go before the first name of our molecule, which would be hexane at this point. So right now we know we have a hexane because there's 6 carbons. We know that we have a methyl at 2. We have a oxo at 3. We have a um, we have an alcohol at 5. So for some reason I'm having a blank. Hydroxy is the prefix for alcohol. So this is why I'm giving you the chart. We can all have bad days. And then 6 is also an aldehyde, which is oxo. And so I noticed something. I noticed that 3 and 6 are the same. So I can lump them together under one name. So instead of 3 oxo and 6 oxo, what I can do is I can say 3, 6 oxo. So I like making a chart like this because then I can go kind of one step at a time. So this wouldn't just be oxo, this would be dioxo. So 2-methyl, 3,6-dioxo hydroxy. Now I've got to get them in alphabetical order, and we have to remember that di does not count for alphabetization. So I'm comparing an M to an O to an H. So H goes first. So it's going to be 5-hydroxy. Oh, 5-hydroxy, 2-methyl, 3,6-dioxo, hexane, 1-oic acid. So that's how I go about naming this. And you can write it linear, or you can keep it like this. We understand what you're saying. 5-hydroxy, 2-methyl, 3,6-dioxo, hexane, 1-oic acid.
I have a quick question.
Yes.
For that one, on the answer key, I'm not sure. I haven't looked at the updated one, but I think on the methyl, it said oxy at the end of it, and I was wondering why.
Uh, that was probably a typo. Let me see. Let me check the, yeah. Uh, yeah. Yeah, it should just say methyl. So that's just a mistype.
All right, perfect. So
Methoxy looks like this. So I was rushing through this, I think. So methoxy would be like that, an oxygen with a methyl off of it. We don't have any methoxys here, so that's a typo.
all right, would we need to know what a methoxy is though?
No. I
All
just
right.
I was on I don't know what I was on. Um, all right. So here we're going to give the base name, our first name, to this six carbon ring. So anytime you see a ring like that, um, we want to give it the first name cyclo, meaning circle. And this is hex. And then one thing to note is that we've got a double bond. So there's going to be some number here for our double bond, right? So that's our first name. We have En for the double bond that's in it. Um, we're going to give the highest, we're going to give the first number to the highest priority, which in this case happens to be our ketone. And so this gets one. And then I have to decide between going this direction or this direction. Since I see two things over here, uh, so two things at two versus one thing at two if I went this direction, I'm going to go this direction because after the first priority, none of the rest of the priorities matter for really anything, right? We sort them by alphabetical order, and for numbering, we just want to give the lowest total number to our branches. So since there'd be two here, that's going to be it's going to give me a lower total number, right? I'm going to have two here instead of one two here. Okay. I think that's the kind of the trickiest part about this one. So that means that our double bond is at two. So we know that. And then I'll go ahead and list all of our different functional groups going off of here. One of the reasons why I made this question the way that it is because I wanted you guys to be able to recognize kind of these groups. There's some common groups that, won't necessarily be there. Someone asked, would it be incorrect if we'd gone the other way around? Yeah, you'll probably lose a point or so. Like if this is worth 4 points, you might lose a point or half a point for going the wrong direction. So you need to go the right direction. And the right direction is giving the lowest total number. So I can sit here and say, if we do black, I have a group at two, a group at two, a group at three, a group at four, two groups at five, and a group of six. If I instead went one, two, three, four, five, six, if I went this way, let's see. I'd have a group at two, two groups at three, a group at four, two groups at five, and a group at six. So the lower total number is the black one, not the garnet one. So I go with the black one. It's a good question. Names have to be very hyper specific, which is kind of annoying. All right, so then I'm gonna just start numbering. There's so many here that I'm just gonna just not worry about priority right now. I'm just gonna write things down. So at two, I have an isopropyl. At three, I have a propyl. At four, I have a tert butyl. At five, I have a 5,5 dimethyl because there's two methyls there. So I have to say that there's one at five and another one at five. And then six amino. So those are all my different groups listed out. I just went one by one. And then I can't forget my highest priority functional group, which becomes the suffix. So that's ene, one, own, because it's a ketone. So it gets the suffix. So now I have to alphabetize these groups. Amino is going to be first. Um, tert butyl is actually going to be second, and that's because with tert butyl, we care about the B. Just like with methyl, we care about the M. So after tert butyl, I don't make the rules. Isopropyl gets to go by the I. whereas propyl would go after dimethyl. So this is a pretty ridiculous name. I probably won't give you this complicated of a thing. Really, I was just trying to show you all of the potential functional groups that you could have to name on the test. So I want to make sure that um, everything that's on this practice test would be something that you'd potentially see on a test, right? I don't want to surprise you with something that you wouldn't see. So 6 amino, 4 tert-butyl, 2 isopropyl, 5,5-dimethyl, 3 propyl, cyclohexene, 1 one. That's one heck of a name. All right, we're about to move on from naming. Do you guys have questions about naming? No? We feel pretty good about it?
So we should recognize that shape as isopropyl.
Yes, I would
I'm
recommend.
on to.
These are really the two big ones, isopropyl and tert-butyl.
Got it.
I would know those. And I would know that isopropyl's naming goes by I and tert-butyl's naming goes by B. Those are really just two common groups. Technically, sec-butyl and isobutyl would be fair game. I talked about them at the same time I talked about isopropyl and tert-butyl, but I'll be honest with you, these two far out represent the other two, so I'm way more likely to ask about them. But I would like for you to know these names and be able to name them. Right? They come up all the time. I mean, I can show you, like, here's an isopropyl right here. That's what IPR stands for. So it'd be good for you to know what that means. Oh, here's a tert-butyl right here. So someone asked, in a cyclohexane, we number the next carbon with the most branches after the highest priority. You can probably make that generalization. I'm trying to think of a situation um, where that wouldn't be the case. But yes, for the technically, it is the lowest total number of branches. So if you went the other direction, the numbers add up higher than if you go this direction. I think that generally works out that like the first place where you find branching would be the place that gets the lower number, right? So here we see like two branches at this direction, but that would be three, whereas here you see two branches here, two functional groups named at two. So that would get priority, I think. Um, that works, but that's not the technical answer. So not alphabetically, just literally just the amount of branches, right? I don't know what that means. So we still have to, once we have all of these listed out, we still have to then alphabetize them. So A for amino, B for butyl, 3 isopropyl, M for methyl, propyl. Like we still at the end have to get all of our prefixes in alphabetical order, but we also have to get the numbering right depending on the lowest total number. So those are independent ideas. The the numbers here have nothing to do with the alphabetization at the end. Um, for numbering, yeah, for numbering it has nothing to do with alphabetically or highest priority after the first priority, highest priority group. Yeah. So, I'm not going to spend a ton of time going through each one of these. I will talk about like some of the places people often get wrong. Or I got it wrong. This is an amide. Uh, anytime you have to be careful if there's a group, like if X is next to a carbonyl, it often gets a different name. So these are often named differently. So you have to be careful about where the carbonyls are. So an amide would be different from just an amine. Notice that this isn't connected to a carbonyl carbon. So this has a different name than this does. Another place that people might get like confused is here. This is not a carboxylic acid. This is an alcohol and a ketone. because the difference between that and this is huge for reasons you don't quite know yet. But uh, that extra carbon here means that this is no longer carboxylic acid. It has to be directly connected to the carbonyl. So those are two different groups. That's one place people will get this wrong, is they'll think that this is a carboxylic acid, or that they'll think that this is an amine with like a ketone or something like that. You can see the difference, right? Here's a carboxylic acid. Um, Other than that, I think the functional groups are pretty straightforward. You guys did a pretty good job with them on the quiz. I anticipate you doing well on the test.
For
Uh,
the sorry, for the benzene, like on the first one it says benzene, but would that also be considered a phenyl group?
yeah, there is a difference between benzene and phenyl, but it's referring to a benzene. A phenyl's, yes, it's fine. Uh,
Okay.
uh, the difference between benzyl and phenyl is like the difference between calling something a methyl group versus methane. Like generally, when we call something benzene, it's the first name of a naming situation. So, like when benzene's the main character, we call it benzene, but when it's a side character, we call it phenyl. Does that make sense? Like
Yes.
when alcohol is the main character, we call it alcohol, but when it's a side character, we call it hydroxy,
Okay. Thank you.
right? When it's like that's really the difference. So I'm cool with both. I mean, don't call an alcohol a hydroxy group, although you could and people do. Um,
How did you name the chlorine in that one?
okay, so I can be pretty flexible about this. So technically, I call this an alkyl halide or an alkyl chloride. Um, because what that's saying is that there's a halogen that's connected to a carbon. So that's kind of the more encompassing name. If you want to just call it a halide, that's okay. Um, I'd I I'd prefer you call it an alkyl halide because I know I probably didn't ask you to learn this, but like if there was a chlorine off a benzene ring, we actually call this an aryl chloride, which you don't need to know that for the test, but I'm just telling you that there's a big difference between that chlorine being on just like a sp3 carbon versus it being on a benzene ring, and we give it a different name because of it. So I would prefer that you call it alkyl halide. Um, yeah, I'm not really asking you what the it's kind of like if I asked you what this was and you just said it was an oxygen hydrogen. I mean, you're not wrong, but that's not what we call that group, right? Because it's connected to the rest of the stuff, we call it an alcohol. So I would just go ahead and call it an alkyl halide. So that's for functional group things. For naming, it's different, right? For naming, you would call it chloro or bromo or whatever, because it's implied that it's part of it. But this functional group is an alkyl halide, um, because it's a halogen on a alkyl group. So just trying to be specific here. So one of the things that's kind of hard for you guys to grasp and think about, and one of the reasons why I come back to functional groups and talk about it all the time, and I care, I'm going to be honest, at the end of the day, this is more important than this, because we're about to get into reactions, and functional groups are called functional groups for a reason. It's because they have a function. Um, and so understanding that like, hey, this amide is different from this amine, and they're going to work in different ways. Right? And we give them different names to kind of help us key into why they're different, right? This is a ketone with an alcohol because it's going to act very differently from a carboxylic acid. So we give them different functional group names because they have different functions. But things with the same functional group all tend to act the same, which is why they get the same name. All right. So, any functional group questions? Cool. Moving on. So what I want here, there's really three big things that you're going to see, or I guess we can make it two categories, is incorrect Vesper shapes. So like this is an incomplete. We recognize what this is, right? What is this? What is that carbon? Anybody have any ideas what we could?
SP3.
It's sp3, but what's special about it? This is sp3 too, but it's not a very special one. What's special about that carbon?
Is it tetrahedral?
Tetrahedral.
Oh, well, so is this sp3 carbon. There's something even more special about it. We've
Is it a
spent like the
chiral
past,
center?
it's a chiral center. You guys notice that? That's a chiral center. So it matters whether, that chlorine is a wedge or a dash, right? It matters whether this is R or S configuration. Those are two different molecules. So this is an incomplete drawing because this needs to be tetrahedral. And it needs to be defined as so, right? That's a chiral center. We need to know whether or not that's a wedge or a dash. Otherwise, we'd have no idea what this molecule actually is. Does that make sense? Meanwhile, that should be flat. That should be trigonal planar is the name. So I would know the name for full credit. It should be flat. You should not see that. I still have Orgo 2 people drawing this, drawing wedges on benzene rings. Doesn't make me happy. Um, but it's something that you guys know. You guys know better. When you get to Orgo 2, you don't do it. All right. There's two other problems I see here. So one thing that's good is to always just kind of check the heteroatoms. So oxygen to be neutral, I'd expect to have two bonds. This oxygen has three bonds on it. So that means it's oversharing. It's positively charged. That'd be my assumption. And then this carbon has five bonds. So that should be, it's actually making me sick to my stomach just looking at it. It's like fingernails on a chalkboard. So just double check, make sure everything else checks out. Everything looks good. All right. So, um, here's a problem here is that should be trigonal planar. So that's a little weird that it would be coming out of the page off of that carbon. Someone asked if this carbon would be positively charged. It's 5. No, this carbon cannot exist. You'll not see 5 bonds on a carbon. It's not positively charged. It just won't exist. It's not a thing. Cannot. It doesn't. It literally doesn't have the enough orbitals to hold that electron. Those amount of electrons. So it's not that it would be positively charged. It just cannot exist. But yeah. That should be trigonal planar. Again, oxygen should have two bonds. This oxygen only has one, so this should have a negative charge on it. You should be able to recognize that pretty quickly. Nitrogen should have three bonds. This nitrogen has one less than three, so it's also negatively charged. This checks out, right? That's a chiral center. It's got a dash. So that's convincing to me. Everything else, well, not everything else. That's also a chiral center. I think I missed that on the answer key. Um, this needs to be tetrahedral. So this is an incomplete drawing. Whether or not this is a wedge or a dash matters. Okay. You guys have any questions about this section? So on a test, I'd want you to be able to put the charges there and to tell me what shape it should be if it's the wrong shape. All right, so this is the fun bit. All right, so the highlighted carbon is the front carbon. So I'm going to rotate that forward. That's going to put the OH up and to the left to make my little Mercedes-Benz logo, hydrogen, and then a methyl down. And then in the back, I have a methyl flat up. Chlorine is going to be to the right, and hydrogen is going to be to the left. All right, so that's my stereocenter. Um, it's pretty easy to translate that directly into a sawhorse. So I make sure that I have the same orientation, hydrogen OH, methyl straight down, chlorine, hydrogen, and methyl. I'll go ahead and just call this methyl so we don't get confused with like just a bond hanging out. It's the same thing. So now we have two different ways to see this, which is, well, you have a million different ways you can try to see a Fischer projection. It's kind of uh, up to you how you want to see it. I showed you a couple different ways yesterday that have worked for some people. If you're still having trouble with it, I might go back through and just really force yourself to do that first method that's a little bit more concrete, where you take a sawhorse, make sure it's rotated the right side around, and you spin bonds so you can get the right orientation. Um, so I'm going to just do it my method here. Essentially, what I'm doing is I know that this should be the back carbon. So my sawhorse has already written the right orientation. So I'm looking at this from the front of the molecule, and I want to make sure I look at it so the chlorine is away from me, it's down. So I'm really looking at it from kind of this angle. I don't know if that's the best drawing. Looking at it from that angle. And so that puts methyl on my right and hydrogen on my left. Now I'm going to move on to the other carbon, the front carbon. And I need that OH to be down away from my perspective. So I'm actually going to look at it from this angle. So I'm standing at the front. I'm looking at it from that angle. I'm standing in front of the molecule at that angle. What's going to be on my left? Any takers?
Methyl.
So methyl's going to actually be on my right.
Yeah, I was gonna say hydrogen.
Hydrogen's going to be on the left because I'm standing at the front of this, looking at this front carbon from kind of this side angle here. And then methyl's going to be on my right. So if it helps, I can show you just for this one how you can draw this in a more suggestive sawhorse. So I already have the front carbon right. That's one thing you have to double check for with the sawhorse, is that the front and the back carbon are right. So if I want to do the sawhorse method, I need that chlorine to be straight down. So I'm gonna draw. I need this orientation for the sawhorse, where I got the two legs up and the things down. So I need that chlorine to be down because it's at the top. And so that would rotate my methyl to the right and the hydrogen to the left, right? If I rotated that direction, the methyl would go here, this would go here, right? They all kind of turn like a bond spinning, which is what it is. And then I need the OH to be down. So the OH would go to the methyl would go to the hydrogen, and the hydrogen would go to OH. So that would give me OH. The methyl would be up here, then hydrogen would be here. And I can trace the methyls on the right, the hydrogens on the left, chlorine OH down. So that's the other way to do it. So you can also use the Newman. Sure. Yeah. Newman's great. Yeah. If you want to, you can use the Newman and put the OH down. The methyl moves right, the OH, the hydrogen here. That's another way to do it, right? Great suggestion. So the one thing you have to worry about if you're doing this method The Newman's actually probably better for this, but I think people are more comfortable with sawhorses. Uh, the one thing you have to be careful if you do this method is this back carbon should be this carbon. If you're in a situation where those carbons have switched, which we might get to, and I'll do an example, um, then you need to flip that whole molecule around. All right. So I'm rotating this molecule to the right, the front of that molecule to the right to get to this wedge dash. It's going to put bromine straight up. It's going to put methyl on a wedge and hydrogen on a dash. Methyl is straight down as well. NH2 is going to be on a wedge. And this carboxylic acid is going to be on a, oh wait, no, I did that backwards. Carboxylic acid is going to be on a wedge and the NH2 is going to be on a dash. Okay, so that's my wedge dash structure. The Newman should be, or the sawhorse should be pretty straightforward. Gonna run out of room. This guy. Maybe up there. So the sawhorse is pretty straight, just copying of the Newman projection. And then methyl is down. All right. So again, okay, so this is one of those tricky ones. This is one of those uh, this methyl should be on a wedge. Right, I rotate this thing to the right. The wedge is still, this methyl is facing to me. There's two methyls. So this one's on a flat. This one's on a wedge. I did that right, right? That looks right to me. Second look. Um, so this is one of the tricky ones, right? This is one of those situations where the carbon in the front is not the carbon in the back, right? There's only one hydrogen in this whole molecule, and it's on this molecule. It's on this. So we have two options. We can either redraw my sawhorse flipped around, right? We can either take this and we can flip everything like this, right? So where the carboxylic acid turns and rotates to the front left. The hydrogen's here, the methyl's here, and the bromine's here. So I can do this. This is one option where now I have the right carbon in the right place. Which you have to be careful about. Or we can just pretend that we're standing in the back here and we're looking at the molecule from the back side, which sounds like it might take a lot of imagination, but it's not as bad as you think it is. So if I'm doing that, I need to look at this molecule like this to get this methyl. Oh, wait, sorry. Sorry, we're looking at this methyl. I need to look at it like, I mean, just straight here to get that methyl down away from me. So if I'm looking at it, if I'm standing at the back of the molecule, that methyl's pointing down, which it is, then the carboxylic acid is going to be on my right. And the NH2 is going to be my left. If I then stay standing in the back and I look at, oh, I've got to get this hydrogen away from me. So I'm going to look at it like that. That puts the bromine on my left and the methyl on my right. So that's how I do it. You can also do the Newman projection or the sawhorse and then spin the bonds around. It means that you have to draw two or three things. So it takes a little bit more time, but it's totally doable. Both should get you the right answer. All right, I'm going to draw a Newman projection. Actually, to be honest, I'll just save time. You don't need to see me draw a Newman projection. We're just going to do Fischer. Spend an extra second on Fischer. All right, so this is one where everything's in the right orientation. Um, I need this aldehyde, which is what CHO is, to be pointing down away from me, but it's in the right orientation. So I'm standing at the front of this molecule. I'm not standing in the back. So I'm going to look at it kind of like this from underneath the molecule to get this top carbon. That puts ethyl on my left and hydrogen on my right. If I do that. Likewise, I need that CH3 point away from me, so I'm going to look at it like this. That puts ethyl on my right and hydrogen on my left. Okay. So our Fischers coming along a little bit. You guys feel better about them after yesterday, maybe getting some more practice. When converting a wedge dash projection to a Newman projection, does it matter which side you place the back substituents on if they're placed in the right orientation when it's eclipsed? Okay. Better, not good. Um, so I think really the key that messes people up is a question like this, where I give the front carbon on a sawhorse and I make it the back carbon on a Fischer. You have to be careful. So you either have to change how you look at it or you um, have to redraw the orientation where everything flips around. For wedge dash structures, does it matter where you place the wedge? All right, so yes. I've talked about this before, but it's good to go over. So the only thing that matters is that the wedge and the dash are together. So like that's fine. That's fine. Good, good, fine. You're actually just kind of looking at like if this is the wedge or dash, you're just kind of either looking at it like that or like that. You're just kind of barely changing how you look at it. What is not okay is for like that is not okay.
Can I ask you quickly about, because I think you might have misunderstood what I was asking.
What's that?
So like on the Newman projection for this question, the third question, like you put the CHO on the top right or top left, like that's my question. Like on the answer key, it shows the CHO is to the left of the ethyl, but can you put it on the right side? Is that like the same
Okay.
type of, because you can rotate it?
So you're saying like if I did this, all right. This is a Newman question.
Yeah.
So here, one of the problems with the Newman is that if you look at this, if you pretended you were looking at this molecule straight down this line, the ethyl and that aldehyde would be on top of each other. The reality is
Yes.
that this molecule looks like this, right?
Yeah.
But that's not really helpful um, or clear. You agree?
Yeah, I agree because you can't see anything.
It does not matter to me if you do it slightly to the right or slightly to the left. The only way you'll lose points is that we really only draw this in two ways. We either draw it eclipsed, where these things are trying to overlap with each other, like very clearly, or we draw them staggered, where this thing is like perfectly in between these two. So as long as I can tell that you're not trying to draw staggered, but you're trying to draw an eclipsed, it does not matter if it's left or right.
Okay, so then would that also apply, like if you were to draw a Newman projection to a wedge dash projection, if you're not like defining which is the side you're supposed to draw on? Like it probably will show in the next set of questions I can ask then.
What do you mean? Yeah, I'm not
So
familiar.
so like the next set of questions we're asked to convert the most stable Newman projection um to the wedge dash notation.
Hmm.
Like in the answer key it shows terbutal on the left side. Would it be correct if you still put it on the right side, on the bottom right, everything like still drawn correctly?
Oh, because I didn't define whether we're
Yeah, there's no left or right defined.
yeah, if I don't define left or right, then it doesn't matter.
Okay, thank you.
I'll tell you on a test I'm going to define left and right.
Okay.
Yeah. Someone said I'm confused because the last one I feel like when you look at the CH3, ethyl's on the left and hydrogen's on the right. Um, so if I'm standing at the front of this molecule and I look down so that CH3's away from me, ethyl's on my right side and hydrogen's on my left. Make sure you're not standing behind the molecule when you imagine this. In this case, we have to be in front of the molecule. Okay. So we're going to move on from Fishers. If you want more Fisher practice, I've got office hours from 11 to 1 today in person. Come see me. Come see in LA. We'll talk Fisher. Um, so most stable Newman projection for the following molecules, then convert them back into stick structure. So yeah, this is kind of the question. This is a poorly written question if I want to grade this easily, because in a test I'm going to define where things are. So the point of this is I want to see if you can rotate bonds in a Newman projection. Here, OH and bromine are clearly the two biggest things, so they need to be anti to each other. So I'll just rotate the front bond here. Doesn't really matter because I haven't defined anything. So OH, hydrogen, hydrogen. And then I'm going to turn the bromine so it's exactly opposite of the OH. And my hydrogens, it doesn't. This one's not too tough because it doesn't really matter where the hydrogens go. Something like this gets a little bit more complicated, although it's not too bad. Again, this is all eclipsed. The biggest thing on the back carbon between a methyl, an NH2, and a tert butyl is the tert butyl. The biggest thing on the front carbon between the methyl hydrogen hydrogen is this methyl. So I just need to rotate this methyl so it's anti to the tert butyl.
Can I ask a question?
What's up?
Why is the tetrahedral higher than the NH2?
It's bigger.
Okay. See.
So this is what a tert butyl looks like. Whereas this is what a methyl looks like, or an amine looks like.
I have a question as well.
Mhm.
On the test, like I know for the quizzes you told us the bulkiest things, but I'm assuming on the exam you're not going to since the review does not have like we have to just know that the terbutyl is more bulky than the methyl.
Okay, so here's this. I want you to be able to do two things. I want you to both be able to recognize that phenols, isopropyls, and tert butyls are particularly bulky things. You shouldn't need A values for those. Then I also expect you to know that A values bigger is bigger. Get what I'm saying?
I'm a little bit confused on the A values. Bigger is bigger. Wait, you're saying?
So on this question, I didn't because I want you to be able to recognize that these things are bulky. So like, I don't need to give you an A value to tell you that this terp butyl group is bigger than this nitrogen. You know, it's clearly bigger. But like, is a methyl bigger than a bromine? Is an ethyl bigger than a amine? You know, like when it starts to get like hairy in the question, I will say, you know, A value, chlorine is, I don't know, 0.96 and CH3 is 1.21 or something like that, right? I don't have them memorized, but I would expect you to know that means that this is bulkier, and we would be listening to that. Does that make sense?
Yes, thank you.
So there's one of two ways I can ask it. I can either give you something that's clearly bulky and just not give you A values, or I can give you A values. I want you to be able to do both. Fair? So recognize that those three things are things that I could give that are bulky. So I'm going to keep the back carbon the same. And I recognize that phenyl and isopropyl are the biggest things on each carbon. So I want to move that phenyl to be opposite of the isopropyl, or the isopropyl will be opposite of the phenyl. That means the bromine's going to rotate down here. The hydrogen's going to rotate where the isopropyl was. So you'd go through the same process if I gave you A values. You would just know that the two biggest A values had to be anti to each other.
And we don't need to know like I don't know how to say it, like gauche and like the different names and stuff like that.
No, I'm not going to ask you about the names.
Okay.
What about if, like, can you just rotate one of the carbons so that the bulkiest groups are just farthest apart from each other? Like, you keep one carbon group the same, and then you just rotate so that the bulkiest groups are farthest apart?
Yeah, that's what I did here. Right. The back carbon, hydrogen, nitrogen, phenyl didn't change. I just rotated the front carbon,
Okay.
right?
Yeah.
And then it wants us to convert this back to stick structure. So on a test, I'll define where you're rotating this. And I won't go through all of these because it's practically the same question. But you could, in this question, you could theoretically flip it both ways. No, I'm not going to ask you. The only thing I would ever ask is at this point is what the most stable Newman projection is. How are we supposed to know methyl is bulkier than amine in this question? It doesn't matter that methyl. Are you talking about this first question or this question here?
I'm talking about, I think that question, it's like, because you have to compare which two are the bulkiest. So like, how would you have known that methyl was more bulky than the amine to compare the two, like to place them across from each other?
That's a great question. Because this amine is attached to that terp butyl group. That terp butyl is clearly the biggest thing, right?
Yeah.
I literally cannot get this across from the terp butyl group. It's on the same carbon.
Oh, wait, I think it might have been the other question then. It was the second question, sorry.
This one?
The middle one, yeah.
This
Or
is the middle one.
oh,
So
so they're on the same one.
you have to
Oh,
look at the
okay.
biggest thing on each carbon. So the biggest thing on this carbon is the terp butyl. The biggest thing on this carbon between these three things is the methyl.
That was my mistake. I
Yeah.
apologize.
No. It's a good, I mean, it's a good question, right? People might be thinking that, but this night I can't move it to be anti because it's connected to the same carbon. that make sense?
Okay, got you.
Um, Gosh, you guys did so well on these. What I will say, two things to keep in mind with the chair structures. One, your chair structure should look good. At this point, the chair structure should look good. There's two ways that I see bad chair structures. It's usually that like these side things are undefined. The lines on the side are undefined. Um, and that just messes everything else up. The other problem I see is people will not make, they'll make these lines too short. So this is actually not a good chair structure here. You end up with this like bond angle that's messed up. The closer side, so if I draw my sidelines first, the one that is closer to the other side, right, that's closer than this, needs to go most of the way to the other side. These two lines need to overlap with each other. Then I can connect them. That's a surefire way to have a fine um, chair structure. Another thing to keep in mind is that isn't left of it, it's clockwise. Or sorry, counterclockwise. Get what I'm saying? So if the OH is up, the methyl needs to be counterclockwise, which would put it here. Um, that's not
Wait, so
really
it would be down?
what?
So it would be down because like if you do the like counterclockwise, because how they're both like pointed up, like where like you put it, that's like going down now.
So this is on a dash, so it's
Oh,
down. Yeah, it has nothing to do with it being on this top carbon or bottom carbon. It's on a dash means that it needs to be down. Yeah, good question. Um, so I guess it's not really a big deal with any of these questions, but it can get kind of confusing. Like if I gave you this methyl instead of the OH, you need to make sure that they have the right orientation, either clockwise or counterclockwise to each other when you do this. Um, Again, this is a place where I could give you A values, right? A values come in handy here too, right? We want bulkier things. We want those to be equatorial. Does anybody have questions about these? You guys did really
Um,
well on the quiz of these, so I don't want to spend time.
so does it matter where you like start on the carbon, like either corner?
Sorry?
Like, does it matter, like, okay, for like the OH, like, say if I put on the top left, does it matter does that matter or no?
Realistically, it doesn't, but in order to keep grading the same, I'm gonna tell you which carbon should be the furthest right carbon.
Oh, okay.
Right? I'm gonna set that boundary, not because it's something that's useful for you, but because it's something that's very useful for grading.
Okay.
So
And
this would be
oh,
the same as this. Oh, what a bad chip structure. Right? If I wanted to do this OH methyl, this is the same, these are the same molecules, right? I've just turned it.
yeah. And does it matter if you go counterclockwise or clockwise when
Yes.
placing the next
Yes, it does.
thing?
So, okay, whereas the top one is right, this is incorrect. And I can show you why. Um, so if I convert this back, well, actually, so if I convert this back into a cyclohexane, what I would get is this. So this is not the same molecule as this,
Oh, okay. Thank you.
right? And I like even if I wanted to turn it in a way, like there's no way I can turn it to get it to line up because the OH and the methyl are in different locations. So the only way I could get the OH and the methyl to line up is by flipping this like a pancake. So I get you'd actually get this. So I'm gonna flip it like this, like a pancake, and then the methyl is up. And you see that this drawing, what is the relationship these two things have to each other? Oh yeah.
They're
Enantiomers?
These are enantiomers actually, right? So by drawing the methyl clockwise instead of counterclockwise, what you've done is you've drawn the enantiomer. So it's not the right molecule. It's the non-reversible mirror image of it. So that's a great question, and that's why we care if it's clockwise or counterclockwise, because yeah, you literally get the enantiomer instead of the actual thing. Great question. Um, Lily asked me a question about this one. I already talked about it, so you can go back.
Wait, no, sorry. I'm talking about the one that's on like this one, the third one that we're no, down. Like for the chair structures.
Oh, actually, it doesn't really matter. So NH2 down, NH2 down. So this has two things. At this point, NH2 and CH3 are pretty similar in size. Um, but this has two things axial, and this only has one thing axial. So I would say that's more stable. It's a numbers game at that point. Does that make sense? Did I lose you?
Yes, no, that makes sense. Thank you.
Okay.
So then we would just have to know that NH2 and methyl
Oops.
is similar in size.
Yeah, I mean, they are.
Okay.
They're pretty close in size, and at that point, it's just what,
Mhm.
having two, three things like it actually becomes there's a way to do it, and we don't go into it. But there's more math that's involved, and there's more than just A values. And you can do all sorts of math to determine like how many methyls would I need to cancel out one tert butyl, kind of deal. We don't get into all of that, but for this case, it's like it should be pretty obvious that you want the two things to be equatorial instead of the one thing.
Okay, thank you.
I'm gonna skip RNS. For some enantiomer diastereomer questions, or sorry, I'm gonna go to a harder RNS question because we're kind of running out of time. Um, this question's pretty easy version of this. Um, right, everything's lined up. Notice these molecules, everything's kind of situated the same way. So I can directly just compare the wedges to the dashes. What does that make this?
Diastometer.
This is a diastereomer, because we have one stereocenter that lines up, we have one stereocenter that doesn't line up, right? Pretty straightforward. So if they were all opposites, they'd be an anti-omer, but since they're not all opposites, but they are different, they're diastereomers, disastereomers. All right.
So wait, basically what would make it an enantiomer is if like they were facing down instead, right? Despite like even if one has a wedge and a dash and they both have wedges, like as long as it's going down, then it would be an enantiomer instead of the the
So enantiomer means all chiral centers are opposite. So this would be an enantiomer if, like the enantiomer of this would look like this. Because that's a wedge, that's a wedge, that's a dash, that's a dash. Right? Everything's completely opposite from each other. Whether or not like it's their relationship, like these two are enantiomers of each other. Whereas this is diastereomer because they're different, right? If this was a wedge too, well, these would be the same molecule. But since they're different, but they're not opposites, they get called diastereomers.
I see the vision.
Sorry?
Oh, I said I see the vision now.
Okay, good. Now this one is harder because these molecules aren't lined up perfectly on each other, right? So um, I don't need to do the RNS of these. I know that these are different from each other, right? Those stereocenters should be they're aligned, so they're different from each other. But I don't know if this stereocenter and this stereocenter are the same or they're different because they're not drawn in the same way. So I can't just say, oh, there's a wedge, so therefore it's the same. No, I have to sit here and find the RNS of this. So this is a good time to talk about finding RNS. So I'm going to focus on the stereocenter with this OH on it in both pictures, and we're going to determine if they're the same or if they're different. This is where RNS is useful. So one bond away, that's an oxygen, and then I have a hydrogen here that's implied, and then I have carbon, carbon. So oxygen's 1, hydrogen's 4, then these two carbons are in contention. This carbon is connected to two other carbons, where this carbon is only connected to one other carbon. So that means that this carbon gets 3 and this carbon gets 2. Luckily, hydrogen is already on a dash, so I can go 1 to 2 to 3. And that gives me my S. So I know that this is an S stereocenter.
I just have a quick question about the question above. I don't know if you said this already, but if it's something simple like that where they're drawn the same, would you just recommend just looking at whether wedges and dashes are the same instead of doing the whole RNS?
If they're drawn the same and I do not ask for RNS, save the time.
Okay, we're gonna be right like 100% of the time.
Yes.
Okay, thank you.
But if they're not drawn the same, you cannot do that.
Okay, thank you.
So like even here, like enough of this stereocenter is drawn the same where I know that this group, like all of the groups off of this stereocenter are all the same. So I can directly compare this wedge to this dash and tell you they're one's gonna be R, one's gonna be S. Like they're gonna be opposites.
Wait, for that question, is it, I thought it would be the other way around for the 2 and the 3.
Why?
Am I?
Oh shoot, what am I doing? I just told you that this is 2, and then I wrote the opposite.
Yeah, wait. So now why is it two now and three? Is it because it has like it's connected to like more carbons?
This carbon is connected to 2 carbons and a hydrogen, or this carbon's connected to one carbon and 2 hydrogens. So if I make my little list, which I would suggest you do, so this is connected to 2 carbons and a hydrogen. Carbon 2 is. Carbon 3 is connected to 1 carbon and 2 hydrogens. This list, the first point of difference is number 2, and a carbon is bigger than a hydrogen, so therefore 2 is bigger than 3. 1, 2, 3. Do this
I'm
one.
sorry, I have a question. So it would be just the carbon that the next carb or the next thing directly of what the carbon is connected to. So you wouldn't take like the O, the double bond into consideration or
Nope.
anything like that, right?
Nope,
Or
not
like the
unless
methyl
these,
group
if
on the
these two
other.
were tied, then I'd keep going, but they're not.
Oh, okay.
Yeah.
Okay. Thank you.
So it's the first point of difference for RNS.
Also, like, how do you choose like to find that like carbon?
This is a chiral,
Like,
so I've got to decide whether or not this chiral center is RNS. So I chose it because this is a carbon connected to 4 different things. So therefore, this is the carbon I start with. And so in order to do the priorities, I have to go 1 bond away in each direction off of this carbon. That's the central point. Yes. So the reason we put 4 on a wedge or a dash is so we can't ignore it. Remember earlier when I said, like, it doesn't matter whether the wedge is on the left or the wedge is on the dash? That's why we put it on 4 on a wedge or a dash, so it doesn't matter how we draw it. I don't know if that makes any sense. Where am I at? So, yeah, the reason it can't be on a flat is because the flats matter which side they're on. And then that 4 doesn't matter with numbering. I go 1 to, honestly, 3 barely matters. You go to 1 to 2 without passing 3.
so
So,
if OH was a dash instead, and like you would have no choice but to make that hydrogen a wedge, and then you would have to flip it.
yes, if OH was on a dash, the hydrogen would be a wedge, and then I'd have to flip this answer, which shows perfectly why, like, if this was a dash and that's a wedge, then I'd get the opposite answer, which gives me the opposite stereocenter, which goes in the enantiomer diastereomer stuff. So yes, by flipping this to a dash, it flips the configuration.
Okay.
All right, so here, likewise, I'm going to go 1, 1 to 2 to 3. I know the hydrogen's on a dash over here somewhere. Again, it doesn't matter whether it's the left or the right because 4 does not play into our circle. But since hydrogen's on a dash, I don't have to rotate anything. I can go 1 to 2 to 3. And this can be S. So this is R, this is S, and I know that these two are opposites as well. So everything in this is an opposite, so it's going to be an enantiomer. I'm going to do one more RNS where we have to do a bond rotation. And then we can talk about boiling points.
I have
So,
a question.
okay, yes.
Could you possibly show us an example of when it would be like a not isomer?
What is their relationship?
They have different numbers of hydrogens, so they are not isomers.
They're not isomers. They have different chemical formulas, so they would not be isomers.
I also have another question. So for the problem we just did, you know how there was like 2 chiral centers?
Yeah.
So can we just pick either or and then number it to find like the R and the S? Like, you know what I mean? I don't know that.
Okay, so technically, this stereocenter is an R stereocenter, and this stereocenter has its own RNS.
Yeah.
So I'd need to find both if I was being asked to find the RNS configuration of this molecule.
Oh, okay, okay. But since we were comparing it between like 2 different types of like molecules, you just need to choose one of the chiral centers?
Yes. I mean, well, no, because I knew that these were opposites already just by looking at them.
Yeah.
I didn't need to find their RNS. I know that they're already opposites. But like the question up here, I would have to find that RNS and I'd also have to find that RNS separately.
Okay.
Right?
Okay.
If I'm asked to find the RNS, then I have to find the RNS. Sometimes you don't need to find RNS to do an enantiomer diastereomer. Like in this case, I didn't need to find RNS because I can tell what's opposite and what's not opposite pretty easily.
Yeah.
Um,
Okay.
so there's gonna be times I ask you for RNS. There's gonna be times when I just ask you an enantiomer diastereomer. There's gonna be times when it doesn't matter whether or not you know RNS to figure out diastereomer and enantiomer, and it saves you time. Um, but there's times when you have to find RNS to figure out diastereomer and enantiomer, like I just did. Does that make sense?
Yeah.
If you're confused, always find RNS. You won't be wrong. Um, let me do this chiral center. So we've got 1, we've got 2, we've got 3, and we've got 4. So what's the problem here?
4 is not on a dash.
4 is not on a dash or a wedge, right? If it was on a wedge, that'd be fine too. But since it's on a flat, call this R. So 2. Since on a flat, I can't do my RNS notation. So I've got to rotate my bond. So again, I'm going to draw all of my wedges and dashes, and I want to rotate 4 ideally to be on a dash. So I'm going to rotate my methyl to be here. So that'll be 4. Then I'm going to take 3, my ethyl, and rotate it up, be with the chlorine. And then this chlorine is going to rotate around to back to 4 to get here. So being able to do that bond rotation when 4 is not on a wedge or a dash is important. And basically, if you think about it, if you zoom out, 4 goes to 3, 3 goes to 1, 1 goes to 4. Everything switches places. Everything changes rotation. It spins like a plane propeller. Then I need to find RNS notation. So I need to trace the shortest path from 1 to 2 without passing over 3. So it's this. That is S. So that is an S stereocenter. So that's about as complicated as it can get, right? Sometimes you'll have to spin it. No, I can spin it either way. Someone asked if I can only spin it clockwise. No, but like if I want to get on a dash, that would be the fastest way to spin it. If I want, I could go counterclockwise. It would just take longer. So someone asked if it's okay for the first priority. The first priority group does not, it can be on anything. The first priority has nothing to do with getting things in the right orientation. Fourth priority only matters. Has to be on a wedge or a dash. Okay, so how do I know which one to lock? If I locked this flat, well then 4 will never be on a wedge or a dash because it's locked. So it doesn't matter which one I lock as long as I don't lock the thing where 4 is at. Right? In this case, I had 2 choices. I can either lock this one or I lock this one. And usually that's going to be the case, right? Because the only time we need to spin it is if 4 is on a flat. So you need to lock the thing that 4 is not on. I wouldn't worry too much about converting Fischer to other projections. Just getting it into Fischer. I'm going to briefly talk about this. So this, in order to compare these two things, I want to get this into a wedge dash out of its chair conformation. So I'm going to draw a cyclohexane, and I'm going to note that this nitrogen is going up. It does not, I'll choose the same carbon that this nitrogen's on for this so I can compare them. Nitrogen's on a wedge, so it's up. or nitrogen's up, so it's on a wedge, right? It's literally pointing up, so it's going to be on a wedge when I convert it into this. Something to be careful about. What relationship does this nitrogen have with this carbon? I have to go clockwise or counterclockwise to get to the carbon.
Clockwise?
Clockwise. So on this projection, that methyl is going to be clockwise. Can I directly compare this to this? Can I say that nitrogen's a wedge, that carbon's a wedge, so that nitrogen's a wedge and that carbon's a dash?
No.
No, I can't because they're not perfectly aligned. So I have two options with a question like this. I can either find R and S of each stereocenter, which is easy and totally possible, and you can do it. Right? The hydrogen's on a dash here, so like 1, 2, 3, right? It's not too hard to find the R and S. It would take you 10 seconds, right? Actually, I'll see how fast I can speed run wedge dash. 1, 2, 3, that's S. 1, 2, 1, 2, 3, that's R turned to S. So it's SS. Or this would be 1, 2, 3. That would be R. This would be 1, 2, 3. That would be S. So I have SS and RS, right? I can sit here and I can very quickly find the stereocenter because the hydrogens are all on wedges and dashes. Pretty easy. Or you can redraw this molecule to align with that molecule. The way I would do that is literally flip it across this central line so the methyl is on the same side, is at the top here, right? I'm literally flipping this like a pancake. And so you get, since you flip it over, the nitrogen's now on a dash and the methyl's on a wedge. And so now I can directly compare that dash wedge, those are opposites, dash dash, these are enantiomers. Or sorry, these are diastereomers, right? Because they're not the same, but they're not perfectly opposites. So those are the two ways you can do it. The first one,
I have a question.
so this would be 1, that's S.
Yeah, for that, do you know that's S because the second one to the left of it, the one to the left of it is the second one? Yeah, all right, perfect.
And then this one, the H is on a wedge, so when I go 1, 2, 3, it's clockwise, but H is on a wedge, so it's got to be S. So the line tells me it's R, but since the hydrogen on the wedge, it's an S. Right.
So there doesn't have to be a fourth.
The hydrogen's the fourth.
Oh,
There's always a fourth because it's a carbon connected to four things. But for the fourth was implied there, yeah, as the hydrogen. Yes. Why does the methyl turn into a wedge when it flips? I'm confused. All right, so any other questions about this stuff? I'm sure there's a million other questions, but we're almost completely out of time. How did I rotate the bonds here? So for this one, I don't have to rotate bonds. I can tell you 1, 1, 2, 3, 4 is the hydrogen on a dash. That's our configuration. For this chiral center, I need to rotate the bond because it goes 1, that should be 2, that should be 3, and that should be 4. So 4 is on a flat. So therefore, I need to lock it. I need to rotate the bond. So I'm going to lock one of my bonds. I'm going to choose to lock this one because I need to rotate 4, so it doesn't make any sense to lock that. So I'm going to just lock 2 in place, redraw my wedges and dashes. 4, I want to rotate back to the bromine to be on the dash. That means the bromine rotates up to be the wedge. This rotates to be the ethyl. So this is 1, 3, 2, or sorry, 4. And I go 1, 2, 3 like this, and that should be R. Is that what you got? Is nitro a functional group you should know? I wouldn't worry about knowing nitro. No. You should know what an amine is, but not necessarily what nitro group is. Boiling points. So our IMFs that I care about, we got polarity, we got hydrogen bond donors and hydrogen bond acceptors. And we've got London dispersion forces. Let's call it dispersion. So really those are kind of the main ideas, right? So let's say boiling point versus water solubility. So for boiling point, we want more intermolecular forces across the board. Higher dispersion forces, more hydrogen bond donors, higher polarity. With water solubility, you want something that's more polar with more hydrogen bond donors, but has lower dispersion forces. You want something smaller. So really, this is where differences play, right? So in this case, we're just asked about boiling point. So I'm looking for bigger things, right? These two things are bigger. This has more hydrogen bond donor and acceptor. It's more polar. So I'd say that's one. This one is more polar than this one. That's two. And then this one has branching, which keeps dispersion forces down. It makes it hard for things to stack on top of each other. Whereas this one can stack on itself better. So that'd be 3. That would be 4. And then this one is purely just a hydrogen bond donating, accepting / polarity question. Right? There's a lot of overlap between polarity and hydrogen bond donating. Generally, the more hydrogen bond donors and acceptors you get, the more polar a molecule is. So this would be 1, 2, 3, 4, just based off of total polarity, total hydrogen bond. Mostly acceptors, but there's a hydrogen bond donor here. All right. Do you guys have questions about anything else? This will be last chance for questions.
Could you see my message?
I see your message. I'll email you back. If you feel confident in all this stuff, should we be decent for the exam? If you were able to do this practice exam without use of help or notes or anything else, and you were able to do it well, and you feel like your answers look like my answers, maybe one thing to do is to take your answers and bring it to an LA or something and double check that like you didn't do something wrong you didn't realize was wrong, even though your answer kind of looks like my answer. So like it's possible that like people draw the wrong chair structure without realizing they drew the wrong chair structure and they can lose points. Or they do something funky without realizing it and it looks enough like my answer that they're okay. I would say bring in your raw answers. So before you checked your answers on mine to an LA or a TA and just have them look over it, make sure it looks okay. If you did the practice test with no help, with no assistance, no key, and you got everything right, and LA looked over it and said everything looked right, you should be golden for the test. If there were some struggles, there were some things that you got confused on, messed up on, it depends. Like, I make mistakes. That happens. I would probably, get a 98 in my own class because, I make mistakes sometimes and I put the wrong thing and that happens. And if you understand why you made that mistake, just go a little bit slower on the test. But if there are things that you did and that were completely wrong, or if you are only getting things right half the time, that would be something to be aware of, right? But in general, this is like a slightly harder version of the real test. Um, okay, so someone asked a hydrogen bond donating question. Even though two stacks better, one has the higher boiling point because of hydrogen bonding. So two has a higher boiling point than three because it has hydrogen bond donating and accepting. They stack pretty equally. One and two. Okay, yeah. The hydrogen bond donating and accepting of this and the total polarity of this outweigh this. Yeah. Really, I'm just looking at branching with like, carbon-carbon chains. So that's really like this isn't really meaningfully a branch. It's actually really small. Um, how does the actual test compare to the in-class lecture review yesterday? That's going to be harder probably than anything on the test. I would say the test looks more like the practice test. The practice test is I truly try to make it like a version 3 of the exam. Can you use pens? Sure. Time.
Do you think if we go to the office hours, will you be able to give us more like diastereomers and enantiomers
I can give
practice?
you more practice problems if you want to come in.
Okay.
That's fine.
Are your office hours in MCH 218 right now?
Yes.
Perfect.
All right. So I will see you guys there. My office hours are officially starting. So I'm going to end this recording and thank you guys for hopping on.